Yeah, how is going with your one-on-one discussion with
Yeah, good.
yeah.
I talked with 2 people. Yeah.
Okay, great.
Yeah, it's good to know what your guys are working on.
Yeah, actually, I guess a lot of people here are very interested in your work. So all of us are urged to know more about this. Yeah.
Yeah, sure. Just please feel free to interrupt and ask any questions. Yeah. Well, I think I have about 45 slides. So
Okay.
we should have lots of time for question and discussions.
Okay, great. I guess we have a lot of people here. So yeah, so maybe we can get a start. And first of all, let me briefly introduce Dr. In Cui. So we are very glad to have In to present his recent brilliant work, shot detection, vision, and language knowledge distillation. I guess many people already know this paper and would like to know more about it. So before the talk, I would like to introduce a little bit more about In. So In is now a research scientist at Google Research, and his research in learning-based computer vision focuses on library efficiency and also multimodal learning. So before joining Google, he received a PhD in computer science from Cornell University and Connecticut in 2019, advised by Professor Sergey Bilangi. In has co-organized several workshops, including COCO visual recognition workshops and the fine-grained visual categorization workshops at major computer vision conferences. So today we are very glad to have In here to present this work. Welcome, In.
Thanks. Okay. Yeah, let me get started. So today I'm going to talk about our recent work on VILD, basically vision and language knowledge distillation, and it's a training method for open vocabulary zero-shot detection. And this is a joint work between AI resident Xiu Ye, who is also the leading author of this project, and also other 2 researchers, Zhong Yi and Wei Cheng from Google Research. Okay. Yeah, so first I will talk about the problem we want to solve, basically zero-shot open vocabulary detection. And the problem setting is usually we allow the model to train on some base categories with detection labels, including the bounding box and the associated class labels. And then we want to see whether, based on this training, the model can detect or segment some novel unseen categories. So as shown in this figure, the toy are the base categories, and the toy elephant or toy with different color attribute are unseen during the training, but we still want the model to detect them correctly. Okay, so how we solve this problem? So the motivation we have is from the dataset collection point of view for large vocabulary detection. So basically, the detection community have witnessed a series of efforts on trying to collect more and larger dataset for detection, because usually dataset collection for detection is very expensive. So the progress is not as fast as the image classification dataset, but the community is slowly moving toward more and more large vocabularies in the dataset. For example, from PASCAL VOC to COCO, those are all common objects. And later we have Objects365, and recently we have Elvis, which focuses on large vocabulary detection with the long-tailed training nature of the images. And by collecting larger dataset, we have to face a problem of long-tail distribution or Zipf's law if we calculate the distribution of the classes among the based on the number of training images or training instances. And here we have a figure showing the number of training instances per category in the Elvis dataset. And we can see among the more than 1,000 classes, the natural object classes follow a long tail distribution. Basically, most of the data are coming from the common objects classes, while most of the classes have underrepresented number of images. And usually, in this case, by this Zipf's law, this means we need to scale exponentially in terms of the total number of images needed for covering the rare categories we want. So this is not a very nice property if we want to scale the object category to a very large number. And this is also very expensive. So our motivation is try to find another way to deal with this issue. And our motivation is basically we want to do the open vocabulary detection as an alternative direction for large vocabulary detection, so that we don't need to collect a huge amount of training data, especially for the rare long tail classes. And we also noticed that there's a recent effort on zero-shot open vocabulary image classification models, such as the CLIP model from OpenAI. And for images, the data collection is much easier because we can leverage the weak labels of web, text, and language pairs. But this is very difficult for the detection because there's no effective way for us to generate weak labels for text queries associated with the regions inside the image. And for CLIP, they collected a dataset of 400 million text image pairs and trained a text encoder and an image encoder based on contrastive learning. And after that, they can use a pre-trained model and append some novel text queries into the text encoder and calculate the dot product between the image feature and the text embeddings to get the prediction of an image. And the CLIP shows a very impressive zero-shot transfer learning ability. For example, achieving over 76 performance on ImageNet. And also, there's another follow-up work from basically in the same time almost from Google called Align. And Align has a larger dataset of 1.8 billion noisy image text pairs, but the quality is believed to be worse than the 400 million data collected in CLIP. And the performance is comparable with CLIP. And differently, the Align leverages the ConvNet architecture, but the best model from CLIP are based on the vision transformers. And the idea of our project is try to borrow the knowledge from this zero-shot image classification model to enable zero-shot detection for open vocabulary. And let me now introduce our main method. So first, the setting for zero-shot detection. So we have the base categories, which the model can be trained on. And we also have the novel categories that are never seen during the training of our detector. And our goal is to achieve good performance on those unseen novel categories while maintaining a reasonable performance on the base categories compared with a fully supervised baseline trained on base categories. And I want to note that the term of zero-shot is very, it's not well defined, and the meaning is also kind of debatable. So our method is zero-shot with respect to the detection dataset, meaning our method does not learn from the detection annotations of novel categories. But since we want to borrow the knowledge from a pre-trained image model like CLIP, so during the training of the CLIP, there might be similar concepts or or classes seen during the as a image level annotation during the training of the clip. So some people may like pursue a more rigorous zero-shot learning where we cannot see any similar concepts even for pre-training of the model. So that's why I want to focus our method is zero-shot with respect to the data set itself. Okay, and our method is based on the two-stage, commonly used two-stage object detector, such as faster RCN or mask RCN. And we choose to use mask RCN because mask RCN also can predict the mask of the object. And since we do not rely on the detection label of novel classes, therefore we also want to see whether our model can do the bounding box detection and also the instance segmentation. So that's why we choose the mask RCN. And the mask RCN is also a mature model for us to use. And we made a small modification of the vanilla mask RCN pipeline. In the mask RCN, they use the class-specific box regression and the mask prediction head, which means for each of the box and the mask prediction, they have the box prediction and the mask prediction for each of the predefined class. Therefore, in our case, this makes it difficult to scale and predict unseen classes. Therefore, we change the box regression head and the mask prediction head to be class agnostic, meaning we only have one generic object categories for the box regression and the mask prediction. Okay, and other than this mask RCN two-stage object detector, there's also—
Hello, Ying. Can I ask a question?
Yeah, sure.
So when you change the class-aware kind of classification or regression to class-agnostic ones, just for a baseline, and how much do you observe? How much performance drop do you observe?
Usually it's 1 AP.
1 AP.
Yeah, 1 to 1.5 AP drop.
Okay, thanks.
Yeah. Okay. And a straightforward approach without using any detection pipeline is to just do the zero-shot detection on the cropped regions of the image. For example, when we have an image and we can get some box proposals from the image, and this can be this model for generating the proposals could be a class agnostic RPN we trained on some like a detection dataset. And after we get the box proposals, we just predict the boxes and then crop and resize the image regions inside the box. And then we feed those cropped region into a image classifier like clip or align to get the class label. So this is a very simple baseline. And we find an interesting thing is that we need to probably ensemble a larger size of the crops to include more context. So we found including another crop of 1.5x box larger than the original predicted box could improve the performance a little bit. So all of this baseline is based on the ensemble of 1x and 1.5x crops. And also this whole pipeline is very similar to the very first method of deep learning based detection called RCNN, region-based ConvNet, which is also based on some non-deep learning based proposal method to like selective search to generate the boxes and then resize the box and feed into an image classifier to get the detection result. But the problem of this method is it is very slow because it has the same problem with RCNN because we need to run multiple times of the inference, basically one inference per box inside the image. So this makes the whole pipeline extremely slow. And another disadvantage is that this is essentially not a detection model, except for the generic box proposal training, because it does not utilize any annotations from the base categories during the training. So that by using the base categories information, probably we can generalize better on the unseen classes. So here comes our method of leveraging the pre-trained zero-shot classification model. So we have the text encoder from a pre-trained clip, and we basically fix the text encoder and do not change anything of the text encoder. And for the image encoder, we have two ways of using it. So we also do not update any text encoder, but we can either do it in an RCNN way to inference on the cropped regions based on the pre-trained RPN, or we can distill the feature from the image encoder on the same region predicted by the RPN, and I will talk about this later. And our first model is called wild text. As the name shows, we basically only use the text models from the align, the text encoder from the align. And compared with the vanilla detector head showing on the left, where we have the N proposals from the RPN, and then we have a detection head to generate the N region embeddings corresponding to the proposals. And after that, we have a linear classifier trained with cross-entropy loss to do the classification. So this is what faster RCN and the mask RCN did. But here we made some small changes. First, we add a projection layer after the same head in the mask RCN, because the feature dimension in clip is different from the feature dimension of a traditional mask RCN. So we want to project them to the same feature dimension so that we can compare with the text encoder from clip. And also the clips feature are all L2 normalized. So we also add an L2 normalization layer after the projection. Therefore, we get, after that, we have N region embeddings. Both each of them are L2 normalized. And after that, we have a background class and also the text embeddings. And the text embeddings are a predefined list of classes or text queries, which are fed into OpenAI's Clips text encoder to get it offline. And the background class is a learnable background class, which are trained during the model training on the base classes. So basically, the training is similar to mask RCN. The only difference is that for the classifier, it's fixed and it's pre-extracted text embeddings, and the only trainable vector is a background vector appended into the classifier. And
hi, Yin.
Hi.
Yeah. So did you try, for example, Robota or BERT kind of model instead of the text encoder in clip? Because we usually prefer to believe so BERT or Robota are stronger than the text encoder in clip, right? So did you have some observation the clip text encoder is better?
Yeah, we tried basically both the traditional word-to-vec embedding and also the BERT, and we have the word-to-vec embedding results. I can show it later. And for BERT, the performance is quite bad, but we are not sure it's because there are some bugs or the performance is bad. We didn't investigate more on that. Yeah. But I think the difference in the in our method is that why we want to use a Clips text encoder is because we think the joint training of a clip by joint training the text and the image data is helpful in our case instead of like a language model purely trained on language. But that's our hypothesis. Yeah. Okay, and we use text prompts similar to the original CLIP paper, but the difference is that in CLIP they usually use a photo of a category, but we add in the scene after at the end of the sentence, and we found that by adding in the scene, we can usually get 2 to 3 AP higher. I think it's 2 AP higher than the text prompt without in the scene. And I think this is interesting and is also related to the detection task. But we didn't do a very comprehensive study on the text prompts, and we believe probably there could be other better text prompts for detection.
Yeah. Did you try at least the ensemble text kind of prompt text embedding in CLIP? Because they, at least for ImageNet, they kind of propose
yeah.
and just average them.
Yes, we ensembled those 63 text prompts basically. Yeah, in the CLIP's paper they have 80 text prompts, and we remove some of the templates that seems to be unrelated to detection, and also for those, and we also add in the scene at the end of the sentence. So that's the difference.
Okay, so finally, the fixed text embeddings are, in fact, the modified and ensembled ones.
Yes, are the ensembled.
Okay.
Yeah.
Okay.
So these text prompts are basically the ensemble of 63 text embeddings.
Okay.
Those are calculated offline. Yeah.
Okay.
Hi, Ying. So what's the criterion to remove the 17 template from the original 80 text prompt?
It's very, I think it's very subjective. So we didn't do a very thorough study, and I think the ensemble of 63 and if we only use this one, I think the performance difference is only 2 to 3 AP. So we didn't like try it very comprehensively, but I think we didn't include this information in the paper, but I can send a follow-up email of what are the 63 text prompts we used.
Okay, that would be great. Yeah.
Okay. And as I said earlier, we have the learnable background embedding, which is basically to deal with the proposals that do not match any labeled categories. And notice that for those this embedding, there could be background classes, or there could be novel object categories. But since we do not see it during the training, so this will be also regarded as background. And I can talk about it later. Basically, the RPN is able to generalize on the unseen classes, even if during the training we treat them as background. Yeah. And then the rest is the same as the CLIP model. We basically do the softmax on the cosine similarity between the region features and the text or background features, and with a temperature same as the CLIP model. Okay, and this is the wild text, and we also have the wild image, which are shown on the right dashed boxes. And the wild image is basically trying to utilize the image encoder from CLIP. And the way to use it is to distill the vision feature on the same region predicted by RPN. So here is how we do this. So we first have a model trained using wild text, and then we take out the RPN part and generalize the RPN box proposals on the basically the training images. And then for those generated bounding boxes, we store them offline into our dataset. And during the training, we then train the model again from the scratch. So the pre-computed proposals are based on the previously trained RPN, and those are for distillation only. And basically, after the prediction of RPN, we have the N bounding box proposals, and we also take out the M pre-computed box proposals we stored offline, and then we append them together with the N proposals from the RPN and feed them together into the head. And also we have the image feature calculated offline from the clip image encoder on those M pre-computed regions. So that after we feed the N plus M boxes into our detection head and do the L2 normalization, we split them again into the N regions corresponding to the RPN proposals and the M regions corresponding to the offline boxes. And the M regions are used for knowledge distillation. So we basically want the M region features to be similar to the M image embeddings on the same region of the image crops. And here we use the L1 loss for the knowledge distillation. And the rest of the head on the N region embeddings is the same as I introduced before, wild text. So basically the left part is wild text and the right part is wild image. And notice that the wild image doesn't contain any trainable weights. So this part only exists during training. During inference, we don't have the right-hand side. We only have the wild text, which is same as the vanilla, basically same as a vanilla mask RCN. So the inference time doesn't change. Okay.
Sorry, I have a naive question on this slide. So why do you use L1 distance for to compute the similarity between your image embeddings? Because when clip was trained, they use a different metric.
Yeah, so this is just for the distillation. So for distillation, I think people usually use L1 or L2 loss, and we tried both and find L1 loss performs better. Yeah, okay. Because this loss is just calculating the difference between the two features. Yeah, it's not the cosine similarity.
Okay, thank you.
Yeah. Okay, so the combined wild text and the wild image model is called the wild, which is our main model.
Hi, may I ask a question?
Sure.
So it seems before your work and the classification part of the object detection is you have a ground truth and it's one hot. And here you just make sure the embedding is close to the clip embedding, and then use the classifier, which is a text embedding from the clip, right?
Mm-hmm. Mm-hmm.
Okay, so basically make sure your vector representation is close to the clip, and then you can directly use clip as text embedding to from the image to text.
Yes, yes.
So my question.
Yeah,
okay,
go ahead.
So my question is, so this requires the distance should be small. So within the range, and then you can use the text embedding. If your distance, so even you train like that, but if your the object embedding distance is a little bit far away to the what clips modeled, and then this may have some problems. So what's the sensitivity of this in terms of the embedding?
Yeah, that's a very good question. So I will have a ablation study of using basically what you are asking is if we only use a wild image alone without wild text. So we have the ablation study of using wild image alone, and the performance will drop. And also for the val text, you mentioned about the one-hot embedding of the target. Actually, the training target is the same. So here in the val text, we are still using the same one-hot embedding of the base categories. But the only difference between the vanilla mask-RCN and ours is that the classifier's weights are fixed in our model. So this is the only difference. And we have a temperature in the softmax. So the cosine similarity, since we have the L2 normalization, the cosine similarity is the same as a dot product. So basically it's same as applying a linear classifier, but the weights of the linear classifier are fixed.
Cool, thanks.
Yeah, thank you. Okay, and here is the overall pipeline, basically for training and inference. So during the training, we have the backbone and the RPN to predict the image regions, and for each of the region features we get, we do the knowledge distillation based on the other M regions from the calculated offline based on the pre-trained clip image encoder, and this is L1 loss. And then if the region are coming from base category, we do the cross entropy loss and train it based on the basically same as the mask-RCN. And this is our training. And for inference, other than base categories, we can append any novel categories, or even we can remove the base categories and append another arbitrary set of text queries and feed them into the text encoder. And notice that we also have the ensemble here based on the text prompts. And after that, we have the list of classes, which may contain the base categories and the novel categories. And we use the same model to do the inference, which are the same as the mask-RCN, generating the ROI region features. And then for each of the feature, we do the classification based on the base and the novel classes, and output the maximum score based on all the classes we have. Okay, so this is an overview of our method. And next, I will talk about an issue we found during training of this model. So we found the val text and the val image. So we have the L1 loss and the cross entropy loss during the training. But we found during training, these two loss often have conflicting objectives, and which cannot be jointly decreased easily. So that's why we also have a model ensembling strategy to improve the performance. So the first thing we found is that if we just ensemble the val text and the clip on the regions, basically we remove the val image part, but we ensemble the RPN boxes. We ensemble the detective boxes with the clip image encoders prediction together with the detector's output. And we found this actually performs quite good, but the performance is very, but the speed is very slow. So that's why we found they have like a conflicting objectives between val text and the val image. And we have a simple solution for that, which is to use two separate heads, one for val text and one for val image. And for the loss function, we basically have two head after this RPN proposal, and we found that this can basically mitigate this issue quite well. And we also have a weighted average of the scores, because here we have two heads. One is based on the distilled feature, and one is based on the detector's feature. And we have the weighted average. So if the class is a base category, we basically give a higher weight on the val text head. And if it's an unseen category, we give higher weights on the val image head. and the details are in our paper. Okay.
Sorry, hi. So I have a follow-up question about your second model. So you used two separate heads for wet text and wet image, right? So during the training, and so during the inference, actually, you will still use these two heads to extract the bound box feature and use this bound box feature to match the text embedding separately, right? Something like this.
Yeah.
I see. And then you do some weighted average. Okay.
Yeah, so this will make the inference time slightly increased because we have an additional head, but the overall increase is very small.
I see. Okay, got it. Okay, thank you. Yeah.
Okay.
Hi, Yan. I'm sorry, may I ask you a question related? Yeah. So here, talk about the conflictions. Could you clarify which one is conflict which one?
Oh yeah, so maybe I think later I will show some result and it will maybe clearer. So basically, if we found if we train with val text only, we can get good performance on the base classes. And if we use distillation or use directly using the Clips image encoder as an RCN, we can get good performance on the unseen rare classes. But if we combine them, actually, we got like a worse performance than the best of those two. So basically, there's some we believe there's like a conflicting training target.
Could you share any insights why there exists such kind of confliction?
Oh, I think probably because here, if we want to do in the val text, if we want to do perfect detection, it's basically mask RCN, and it has nothing to do with distillation, and it has nothing to do on forcing the features to be comparable to the text to the image features here. So therefore, it does pretty well on the trained scene classes, but it generalizes poorly on the unseen classes because it cannot fully utilize the image encoder in Clip. And on the other hand, if for the wild image, if we do a perfect job, we basically generate the same features as the Clip's image encoder. But at the same time, we cannot do good on the detection training side of the base classes because we basically do not utilize any training signal on the detector.
So I'm trying to have imagine a case where if you're seeing the number of the scene classes increases, and then the confliction should be reduced, right?
Yeah, that's possible. Yeah, I think so.
So in that sense, one reason for this kind of confliction, maybe because of the number of the scene classes is so small, such that on the text embedding part, you have a very discrete representation in the model space.
Yes.
You only have a few sample prototype over there to represent the scene classes.
But, yes. Okay, yeah,
so
I agree. Yeah, I think that's a very good point because the text embeddings only contain a very small set of the classes, but actually the text encoder can do any arbitrary text embeddings. So this only covers a very small set in the whole output space, and it's hard for this to generalize to other unseen categories. So that's why we need to leverage more on distilling the image embeddings. But if the text embeddings contains a large amount of classes or different variants or diverse set of text queries, then probably doing this val text alone can guarantee a good generalization of unseen text.
Okay, cool. Thanks.
Yeah.
Okay. Yeah, I also have a related question here. So if you have two separate heads, then how will you use the while the image head feature to do detection, because for this head, then it does not understand background anymore.
You mean, oh, okay. You mean for this head, it does. So I think part of the background is also coming from the val text, so it also contains background, and also during training of the RPN, it also has the concept of the background.
I mean, for kind of really for when you do detection, when you output the predictions, how do you kind of for this head? How does how do you determine whether this is a background or in fact this is a foreground for this wild image head?
Yeah, for this detail, I think I couldn't remember clearly what we did. I think for wild image, we probably don't have the background weights. So the background is decided based on the RPN scores, because RPN also have a objectness score.
Okay, thanks.
Yeah, but yeah, I can check that later. Yeah, if you send me an email. Yeah.
Okay.
Hi, Ying. So I also sorry. I also have a follow-up question. So because we have just talked about the background category in your wild text, so and also Yingpeng just also mentioned about the feature space for the textual concept here. So I'm wondering whether you observed that the background embedding here will affect the feature space for the visual concept. So because if we assume that you initialized the background embedding to some visual concept from the unseen categories, and then you will probably lay some hit that push the visual feature of the unseen category to the background embedding to some extent, right?
Yeah.
So in this sense, do you think the background embedding is removable, or how to maybe improve this by design different, for example, use different type of background embedding?
Yeah, I think that's a good question, and I actually honestly don't know the answer. I think the background is how to deal with the background for open vocabulary is like an open question. So here we basically assume the background can capture anything like unseen and real background classes, and during the inference, since we have the unseen text embeddings, and we basically hope those unseen text embeddings will have a higher score on the regions, on the unseen regions compared with the background embedding. And we found in our experiment that that's also true. But there could be better ways. For example, one thing we tried is to use sigmoid loss instead of the softmax loss, so that we can remove the background embedding, because in the sigmoid, each class is basically a binary classification of whether the embedding is belonging to this class or not, which makes more sense to this softmax loss. But we found the sigmoid loss actually performs very bad, and this could be because the clip model was also trained with softmax, so the distribution is kind of hard to match. But yeah, but this is basically the simplest and the simple and also works well. It's a simple solution we adopted. Yeah.
I see. Okay. Yeah. Thank you.
Right. Okay, I will move to the results. Sure. So for the benchmarks, I think we are using the Elvis V1 dataset, which contains over 1,200 categories. And we have frequent and common categories as the base categories, which have, all of them have at least 100 images, training images per class. And all the rare classes are regarded as novel classes, and we remove the annotation for rare classes from the dataset during training. And this contains over 300 classes, and each of them have less than 10 images per class. And we believe this is a realistic setting because for open vocabulary detection, we are interested in scaling to larger vocabularies. So those vocabularies that are not included during training are often rare classes that are rare in natural world. So that's why we basically hold out the rare classes in LVIS as a benchmark. And also this enables us to compare with the supervised baseline when we include the rare annotations to see what's the gap between the supervised and this open vocabulary method. And we use APR, APC, and APF corresponding to 3 frequent, common, and rare classes. And first of all, we tried to verify our idea. We calculate the RPN's average recall on novel categories. So the first line is the RPN trained only on the base classes by removing the rare classes. And the second one is the same RPN trained on the whole data set with the full annotation. And we can see here the AR is basically similar, which means that the RPN is able to generalize even the categories are not seen during the training. So basically means the RPN did a pretty good job on detecting generic objects. So this makes sure the rare boxes can be predicted correctly, mostly correctly by RPN. This enables the successfulness of our follow-up detection heads. Okay, and the second experiment is what I mentioned earlier about the simple baseline of classifying image regions with the original CLIP model. And here we have the supervised baseline by training on base class only. And for sure, because during the training we do not see rare classes, so the AP is 0 because all of them are treated as background. And for the CLIP on cropped regions, this is an RCNN style model. And we can see the APR is already pretty good, 13, which is actually better than a supervised baseline trained on the full data set. But of course, the AP for common and the frequent objects are quite low because this model doesn't train on any of the LVIS annotations. It just has the LVIS class embeddings. But this makes us curious to why the APR is better than the supervised baseline, and also the APR is better than the APF. And I think for the first question, probably the training number of training images for the rare classes are very small. Therefore, there's a very severe data imbalance problem during the training. So for example, if we just use a vanilla supervised baseline, the performance on rare class are quite bad. And if we do some repeat factor sampling baseline to upsample the rare classes, we can improve the performance, but the performance is still low. But for this CLIP on cropped regions baseline, we do not have such an imbalance problem. Therefore, the performance on rare class are also can be like quite good. And also we believe the reason for rare classes to be better than frequent is probably due to the fact that the rare classes are usually more fine-grained. So the description of the class is more precise than the frequent. For example, we found both classes bear and the grizzly are in the LVIS dataset, and the bear is a very common class and a very generic class, and it's in the frequent class. But the grizzly is like a specific species of a bear, but it's in the rare. So we often found the CLIP model tend to predict the species of the bear instead of like a generic class of bear. So there are some class confusions in the common classes. So we believe that's probably why the frequent class performance is lower. Okay, and then I want to mention about our supervised baseline. It's a very strong baseline of ResNet-50 FPN, which uses large-scale jittering and a longer training schedule. And this baseline is formally introduced in our another paper, copy-based data augmentation paper, and it's also recently adopted by Detection 2, and there's a Facebook AI blog post on this. So in general, we can have more than 6 AP improvement on the baseline if we train the model longer and use more aggressive data augmentation of large-scale jittering. And for more details, you can take a look at the paper and also the Facebook's blog. Okay, and for our model val text, the performance is about 10 AP, which is a bit lower than the clip on cropped regions. But since our model is trained on base categories, so the AP on common and frequent base classes are pretty high. So this is basically a more like a utilizable model because we do not hurt on the thin classes during the training. And we also notice that our val text outperforms the globe text embedding. So these models are the same, except the text embeddings are different. One is using the globe word-to-vec text embedding. Another is using the Eclipse text encoder for generating text embedding. And we also have the veiled image model, which is the distillation only model. And notice that this model does not train on any annotations of the detection dataset. The only loss we have is the L1 distillation loss. So presumably the model of the performance of veiled image should be similar of clip on cropped regions, because the clip on cropped regions is actually the teacher model for the image, for the veiled image. And also we have the veiled model, which is a combination of text and image, and we use a weight of 0.5, which basically gives the same weight of the text and image part during the training of the loss. And at the final row is our supervised baseline. And we can see on AP for unseen rare classes, we can outperform the strong supervised baseline. But the overall AP is still a little bit lower. And this gives us an ablation study of L1 loss and L2 loss for distillation, and also different weights for distillation loss. And we can see the overall, the L2 loss does better job on the thin classes, base classes, but performs poorly on unseen classes. Since we care more about the unseen novel categories, so we adopt the L1 loss. And finally, this is our model, the best performing model with the ensemble. So basically using two different heads, one for veiled text and one for veiled image. So we can see that the confronting issue is better solved here because the APR is almost the same, but we can have better APC and APF. So that means we can better learn from labeled base categories. And the best performing model is actually the ensemble of veiled text and the clip on cropped regions, which is basically the ensemble of veiled text and the teacher model of veiled image. But this model is quite slow, which is more than 600 times slower, because we need to do the inference for each of the detected boxes. Okay, and this is a result of a better backbone ResNet-152. This is ResNet-50. So here we have 16.6, and now we have 18.7. So we can have about 2 AP improvement by using ResNet-152. And we can also do transfer to other detection dataset without any fine-tuning. So this is very simple. We can just take the Elvis trained model and just replace the classifier by the category embeddings of a given dataset, and then just do the inference. So this is a fine-tuning free transfer. And we notice a small gap between this fine-tuning free model and the fine-tuning of the linear classifier. And certainly there's a larger gap between this model and the fully supervised baseline. But overall, we believe the performance are exciting because we can achieve 36.6 by this simple replacing classifier on COCO. And here are some qualitative examples. So I will basically skip. And I will talk more about the on-the-fly interactive detection. Oh, I think we are close to the end of the time. Maybe, is that possible? I can take maybe 5 minutes.
Sure. Yeah, no problem. Yeah.
Okay. Yeah. So yeah, for the questions, probably we can do offline. You can just send me an email or during our one-on-one. Okay, and so we can do also some other applications that traditional detector cannot do. For example, on-the-fly interactive detection. So here we just basically do the detection on the base categories, but after the detection, since we have the detected bounding boxes and also the features in each detected region, we can do the on-the-fly free-form text embeddings to calculate their cosine similarity. So this is quite fast because we only need to do the text inference and also the dot product between the pre-calculated region features. For example, in this image, we show the 2 text squares, yellow dog and the black and white dog, and we can see the classifier is able to distinguish between these two and also the dog species. And in this image, we have a longer sentence as a text embedding. For example, we have the different parts of the bird and associate different colors to the body and head parts of the bird. And we can see the model is also be able to correctly classify and associate the color and the parts of the detected bird, which we believe is very exciting results. And also we can do a similar thing of expansion on the dataset vocabulary because we want to do large vocabulary detection. And the expansion is very simple. So for example, if we have a list of vocabulary and a list of attribute sets we want to expand, we just do this by calculating the probability of on each of the attributes and each of the base classes or any class embeddings, and then we just multiply them together, assuming the attributes and the class vocabulary are independent. So this simple way gives us a very efficient expansion. For example, we can expand the P vocabularies into P times Q vocabularies basically by multiplying the class by the number of attributes we have. And here is an example. So for example, we have the detected fruits here, like orange, lemon, and kiwi, and we also add 11 colors on all the Elvis vocabularies, and we can see all the seems to most of the colors can be detected correctly. For example, yellow lemon, red orange, and this dark orange, and the green kiwi. So it's also interesting that, for example, for the upper right corner boxes, the model can also distinguish between dark orange and the light orange color. So the model seems to be doing a pretty good job on the color attributes. And also we tried it on COP200 fine-grained dataset by expanding the category with all the 200 bird species. And we can see those are the correct detections. And this is a failure case. So the detection species is wrong. And notice also the probability are much lower because we do the multiplication between the attribute probability and the class probability. And those are some failure cases. On the left-hand side, we miss the detection of this elevator car. And notice that all those classes, missed class, detected classes are novel classes in Elvis. And in this example, the whole object should be a waffle iron, but we misdetected the upper part as a calculator. Okay. And now I want to show some new results that are not covered in our paper. So the first one is we also we are doing some comparison with existing zero-shot detection methods on COCO. So the previously we did not do this experiment was because we found people are all using different splits of COCO dataset. Basically, each of the paper are different from the previous paper on the COCO dataset, which makes it very difficult to compare. Therefore, here we just pick the best method on paper with code leaderboard. And we can see here with the val text model alone, without any distillation, we can already outperform this state-of-the-art method by training on COCO split. So basically, we have 65 syn classes and 15 unsyn classes. And notice that here the comparison is a fair comparison because we do not use wild image, which does not involve any pre-trained image classifier. So what we do is just to fix the linear classifier by using the clips text embedding. And especially on the recall, we can do a much better job. For example, on the unsyn and the syn classes, the recall are much higher than the previous state-of-the-art. Okay, and also I mentioned the align model. Since clip model, since the clip model was not fully open sourced, so at the time of our paper, we only used the VITB 32 of the clip model for the image distillation. But since we're at Google and we can leverage the pre-trained align model internally at Google, and we also tried the align model by using the EfficientNet B7 model of align, and also the detector backbone. We also upgraded to from ResNet-152 to EfficientNet B7, and with the same wild ensemble method. And here we see a drastic increase of APR on Elvis for novel classes. And we also have some smaller improvement on base classes, which are due to the better detector backbone. And I think if we use transformer-based backbone, the performance could be even higher, probably. And compared with the supervised baseline of EfficientNet B7 backbone, we can get more than 10 AP improvement on novel classes and the comparable performance on the base classes. I think this is a very strong signal. That means basically, if we don't have enough training example on our data set, probably this open vocabulary detection can do a better job than even the supervised baseline. I think this is a very encouraging result. And we also do some visualization of this pre-trained model. So this is the input image, and on the right are the detected class agnostic boxes of the objects. And here are the input text we input to the model as a text embeddings. For example, we choose to add some attributes of the classes like black and white flip-flop to see whether the model can distinguish them, and also some pink striped or plain pink umbrella by adding more attributes. And here are the top 5 predictions. So for example, I think all of our predictions are correct. So the left column is the box, and the middle column are the mask and the corresponding location in the original image, and the rightmost column are the probability distribution among 17 text embedding queries. So for example, this one is detected as blue patterned umbrella and better than other, for example, pink striped umbrella. And we can also see the mask for the umbrella and the shoes are also quite good. And maybe another example is, for example, yeah, and for example, this one. So we also have the bracelet and the necklace, and you can see the model is able to correctly predict this is a bracelet. And later we also have a necklace here, and the model is also able to correctly predict them. And also the street signs, and these two umbrellas. So one is pink striped umbrella, and another is plain pink umbrella. So the model is also able to distinguish the pattern and the pattern of the umbrella. Okay. Yeah, so that's all of our presentation. So some conclusions. So we propose wild and open vocabulary detection method by distilling the knowledge from zero-shot image classification model, and we achieve better than supervised counterpart performance on unseen rare classes on the LVS dataset. And this model enables us to append the new classes without the retraining of the detector, which is an ideal feature we want to have. And we can also do transfer to other datasets without fine-tuning by just replacing the classifier. And this also enables us to use free-form text as the text queries for detection. And finally, our motivation, and we want to see an alternative for detecting long-tailed classes rather than scaling up the detection dataset by collecting probably exponentially more images to cover them. Okay, that's all. Thank you.
Yes, thanks a lot for the great talk. So I think all of us are very intrigued to your work. This very brilliant work. So for the interest of time, so maybe we have to end here. But if you have any further questions to ask, please feel free to send an email to him or set up some one-on-one discussion if he have more slots. So yeah, so let's thank Ian again for the great presentation.
Yeah, thank you.
Yeah,
and I will also share the slides maybe in PDF format to you.
Okay, that would be great. Yeah, thank you, Ian. Yeah,
thank you.
Yeah, thank you, Ian.
Okay, bye. Thank you.